In the video cell-level dose-response curves, we discussed what a dose response would look like in a graph as you increase the amount of agonists in a system. In this video, we are going to discuss ways of quantifying a dose response. The learning objectives for this lesson are to describe how to measure or quantify a response based on measurements from either an individual or a population, and discuss how the therapeutic index is used to determine drug safety and some of the pitfalls for using this metric. Let's do a quick review of key terms we have covered. Ligands are chemicals which bind receptors, triggering a response. The response depends on the affinity, efficacy, and potency of a ligand. Affinity describes how well a ligand binds a receptor. Efficacy describes how well a ligand elicits a response. Potency is measured by how much of a ligand you need to get a desired response. One of the most critical concepts in pharmacology and toxicology is that depending on your dose, you may see a therapeutic response or a toxic response. An overdose of water can be deadly, while low doses of digitoxin from the foxglove plant are used to treat heart conditions. Therefore, it is very important to quantify a response of a drug or toxin as the dose increases and use the dose-response curve to evaluate chemical safety. There are two ways to quantify a dose response, based on if the response is measured in an individual or a population. When you look at an individual's response, such as a rat or human subject given a new drug, you will observe a graded response that should increase or decrease with increasing dose. This means you measure a dose on a continuous scale. If you have an entire population exposed to a toxin or cancer treatment, you will use a quantile response, since the data represented is the percent of the population that had an observable effect at a given dose. A quantile response means we are looking at varying observed effects rather than a continuous effect. Let's start by looking at the graded dose-response relationship. The y-axis has the response, Q, as a percent of the maximum response, Qmax. As previously discussed, an agonist that elicits a response below Qmax is called a partial agonist, while a full agonist reaches Qmax. The x-axis is the dose of the drug or toxicant. We can see that with increasing dose of ligand, there is an increase in the percent of a response. This relationship is not linear, but curves until it reaches a plateau, demonstrating how small changes in dose at low concentrations can have a major impact on the observed effect. The effective dose that elicits a 50% response is called the ED50. The ED50 is a common calculation to compare drug potency. You may come across the percent response represented as a fractional response, also described as Q over Qmax. This term is used when discussing the concentration of receptors occupied by ligands and how this relates to the measured response. To get more details about this topic, read about receptor occupancy theory and models in the assigned textbook Pharmacology, Principles and Practice by Hacker, Messer, and Bachman, 2009. Curves are not easy to work with when comparing different drugs, so pharmacologists and toxicologists will take the log of the drug concentration and plot it against the observed effect. You end up with a sigmoidal curve. Keep in mind that when using the log concentration, the linear part of a graph is actually a very large range of doses. Now we can look at how the slope, height, and position on the x-axis relates to the affinity, potency, and efficacy of a drug. First, let's look at potency. Shifting the plot to the right on the x-axis would mean you needed a higher dose to reach the same effect, resulting in a decrease in potency, yet the drug can still reach a maximum response if it is a full agonist. If the response is less than the maximum effect, then your ligand has a lower intrinsic efficacy, even at high concentrations. The slope relates to the affinity of the ligand, with a steep slope correlating with a higher affinity, a lower KD, and a higher potency. Now we will look at the quantile dose-response relationship, which is used to look at how a population as a whole responds to a drug. The percent of individuals responding is on the y-axis, and the log of the drug concentration is on the x-axis. After plotting the percent of people who have a therapeutic response to a drug with increasing dose, we get a bell curve, with the center representing the mean of the population. The ED50 is the dose when 50% of the population has a therapeutic response to the drug. If we keep giving higher doses, the toxicity range for the drug starts, again represented by a bell curve. The TD50 is the dose when 50% of the population has a toxic response to the drug. Two interesting populations are the hypersensitive and resistant individuals. Hypersensitive people may get sick at very low doses, making the drug unsafe, while the drug is ineffective on resistant individuals, making the drug useless. A bell curve has 68% of the population 1 standard deviation away from the mean, and 95% of the population 2 standard deviations from the mean. This is helpful to keep in mind as we compare bell curves to get an idea of the proportion of the population that may have a therapeutic response or toxic response. You may have noticed that the ED50 on the bell curve may not represent 50% of the individuals responding on the y-axis. This is because ED50 is when half the population, represented as the area under the curve for half of the bell curve, has a response to a drug or toxin. You may see a very gradual response, which would mean the bell curve may not go above the maximum response of 10% of the total population for any given dose. In the next slide, we will look at another way to view data for a population response. Here we have the log of the dose on the x-axis, and the left y-axis is the percent of individuals responding to a drug, and now the right y-axis is the cumulative response for the whole population. Graphing a cumulative response means the graph will show the percent of people who had a response up to a certain dose, rather than the percent of people who had a response at a specific dose. The cumulative plot looks like a sigmoidal curve, and now the ED50 matches with 50% of the population responding. The percent of individuals responding, blue graph, and the cumulative percent of the population responding, green graph, are both useful graphs when comparing drugs or toxins. Let's look at some examples. How the bell curves for a therapeutic range and a toxic range overlap helps determine how safe and effective a drug may be. To help quantify how safe a chemical is, the therapeutic index, or TI, is calculated by dividing the TD50 by the ED50. Ideally, a drug's toxic range should be far above the therapeutic range, resulting in a high TI. If the toxic range is close to the therapeutic range, there is an overlap in the curves, and now the effective dose for some individuals will cause toxicity in others. The therapeutic index of drug A is 10, while the therapeutic index for drug B is 5, suggesting that drug A is the ideal choice. But if we look at the shapes of the curves, drug A has more overlap in the therapeutic range and toxic range than drug B, making drug B a possible better choice. Of course, many things play into how safe a drug or how lethal a toxin may be, including the route of administration, how safe its metabolites are, and how quickly it is eliminated from the body. Here is another way to look at overlapping bell curves. In this graph, we have the corresponding cumulative plots for each bell curve. When 90% of the population has a therapeutic response, what percent of the population has a toxic response? First, look at the dose at which 90% of the population has a therapeutic response, also called the ED90. This dose is included in the toxic response bell curve and correlates with 10% of the cumulative response for the population. Therefore, the ED50 is the same as the TD10, and 10% of the population is having a toxic response to a drug while 90% is having a therapeutic response. Would you call this drug safe? Along with the pharmacokinetics of a drug or toxicant, the affinity, potency, and efficacy needs to be considered when evaluating drug safety or conducting a contaminant risk assessment. We have now covered the fundamentals of pharmacodynamics and toxicodynamics. Use this information to critically evaluate peer-reviewed papers and case studies, and to develop your own experiments to test drug and toxicant mechanisms as you progress through your studies of pharmacology and toxicology.